Engineering Department, A.D. Patel Institute of Technology, a Constituent College of CVM University. I welcome all of you in this STTP sponsored by AICTE under AQIS. For today's first section, our session expert is Dr. Prabal Talukdar. He is just joining. So as soon as he'll join, we'll start the session. So stay connected meanwhile. Good morning, sir.
Good morning, sir. I think you are mute. So शायद आप म्यूट पे हैं.
Yes. Good morning, Mitesh. Good morning, everyone.
Good morning, sir. Good morning.
So our session expert has joined, and I would like to invite Dr. Mitesh Shah sir to introduce our expert for this session, Dr. Prabal Talukdar. Over to Mitesh Shah sir.
So very good morning to all, and first of all, very warm welcome to today's speaker, Dr. Prabal Talukdar sir. And today is the third day for the AICT AQIS sponsored faculty development program organized by Department of Mechanical Engineering, AD Patel Institute of Technology, Constituent College of CVM University, and located in Anand, Gujarat. So before I request to sir to start his presentations, I would like to introduce him. Dr. Prabal Talukdar sir is currently working as a professor in the Department of. Prior to this, he was working as a postdoctorate fellow at the University of Saskatchewan during 2005 to 2006, Canada, and University of Erlangen, Nuremberg, 2002 to 2005, Germany. He did his MTech and PhD from IIT Guwahati and BE from Assam Engineering College. He has been working as a visiting professor or scientist at the University of Freiburg, Germany, and University of Saskatchewan, Canada, in the past several years. His area of interest includes computational fluid dynamics, heat transfer, radiation heat transfer in participating media, convective drying, inverse heat transfer, heat and mass transfer in porous media, heat transfer from combustion in reheating furnaces, thermomechanical analysis in continuous casting, heat and mass transfer through fire protective clothing. So he is having a lot of experience. He is a good researcher also. He has published more than 70 publications in various reputed journals. He has handled 10 projects and he has attended 50 plus conferences also. Thank you very much for being with us. I request Prabal sir to start his session.
Thank you, Mitesh, for the introduction. I'll first share my screen, then just let me know if there is a problem. I think present now, and your entire screen. So the screen is visible, Mitesh?
Yes, sir, it is coming.
Okay. So good morning, everyone, all the participants. Today's topic I have chosen because this is a topic I have been working in the past few years with two of my PhD students. One student has just been graduated, and one student is still working in this area. So this is a relatively new field for us because we have worked in this field for about 4 years or 5 years from now. So in a research, working in the field for 4 or 5 years, although it sounds to be very long amount of time, actually it's not a long amount of time because in order to have good understanding in certain topics, you need to spend even more amount of time. So we have gathered some experience in this area, and most importantly, we have been working in this area with industry because of this. Whatever research we have been doing in this area are basically industry oriented. So it has a direct application or direct implementation in the industry point of view. So that's the best part of this research what we have been doing. It's CFD modeling, but at the same time it's not that every time we are solving momentum equation, because when you say CFD modeling, then there should be some fluid dynamics. But it's not that in all problem, whatever we will be discussing today, there is a flow flow associated in most of the, or at least there are a few problems where we have not considered convections. It's basically only conduction heat transfer and conduction heat transfer. So, but then there are problems where we have flow also. But this is not very hardcore flow problem, but it's mostly a heat transfer problem in continuous casting, where you have solidification phenomena which happens in a casting process. So the outline of the presentation, I'll discuss about continuous casting, which you may not be having much idea about continuous casting. Then the engineering issues which are important in continuous casting process. Then the associated CFD models and CFD problems which we have worked in this area. Then the different phases of research which we have been undergoing in the recent past, and the summary of this work. So if you have gone to some steel industry, you can see the continuous casting process. So there is a small schematic diagram which I have with you to share. If you see, let me use my So this is a liquid. This is a copper mold here. Mold is basically a.
Excuse me, sir.
Yeah.
Your slides are not changing. In case you are doing so.
Yeah.
Yes. Now
it happens when I take a full screen mode. Then it happens like that. Then I have to do it in a presenter like this mode. This is now, I think, visible, right?
Yes, sir.
Like
yes, sir. It is visible.
Yeah. So your screen will be slightly smaller, but then we have to go with this one.
It's okay, sir.
Some other view is possible. Let me check. Now, do you see some changes?
Yes, sir.
Changing, right?
Yes, sir.
Can you just change it?
Sir, can you change it once so that
I'm changing now. Do you see
no,
some
it is
changing?
not changing, sir. It is at your third slide only.
Okay. Then I'll just leave that. I'll go like this way. I'll try to make it as big as possible.
सर एक बार F5 करके देख लीजिए. F5.
In my screen, this is becoming full screen, but you are not able to see the changes.
Oh, okay.
That I have seen in some other presentation also. I don't know why it happens with some software. So only possibility is like I try to make it as big as possible. Now I think should not be a problem.
It is visible, sir. Fine.
It's visible and big also, right? Only I lose little bit of spaces in top and side. Okay. So this is a continuous casting process. This one, the presenter, I think I can. You can see my cursor, right? Rotating here. I mean, going here and there.
Yes.
You can see my mouse cursor. Okay, I'll manage with this one. So this is a copper mold. Mold are basically made of copper because of you need a high heat transfer rate to the copper mold, and then there's a liquid metal which is poured from a tundis. This is called there is another part which is called tundis, from which the liquid metal is poured through a jet. So that is not shown here because our area of interest is basically the heat transfer and solidification process inside the mold. So that is why we have taken this portion. So this mold is sort of, this is like a cut section view. The mold is basically a rectangular structure which both the top and bottom are open. This is not a closed space. It's like a sort of a rectangular channel, right, which is kept in a vertical direction. So liquid metal is poured here, and then outside the copper mold we have cooling water. So the main idea is that this liquid metal needs to be solidified, and then in order to make slab or billet or depending on its size, this solidified metal is called, if it's a bigger kind of cross section, then it is called slab. If it's a smaller cross sections, it's called billet, right? So there are different nomenclatures are there, but these are basically liquid metal which is solidified to a which is solidified, and then they are basically steel, which we use in our various applications. So in order to solidify this molten liquid or molten liquid metal, basically liquid cooling water has been circulated towards the outer side of the copper mold, right? And because of the cold water which is circulated in the outer side, there is a heat transfer process from the molten liquid to the cold fluid, and because of that, this molten liquid, it gets converted to solidified steel, right? So that's it shown here. The gradually what happens inside the mold, you will find a solidified strand which is forming at the boundary of the mold, and after that, since there is already a solidified strand, then it actually gets a sort of a protection now, because the outside periphery is all solid and inside you have a molten metal. So then you don't need a sort of a guidance here. The mold is not required after this one. The solidified strand itself sort of controls the liquid metal, and then gradually it comes downward. But of course, like at the same time, now this is open to atmosphere, so you are basically spraying water here so that there are more heat transfer, because having heat transfer through copper mold is not very high, because you have conductive resistance because of the copper mold. But this is now open to atmosphere. You are spraying water here, so your heat transfer rate is quite high here, right? Because of that, desolidification also increases in this portion, and then gradually all liquid is converted to solid, and after several meters, of course, after several meters, you'll get a solidified cell, which is basically your slab or billet or bloom, whatever nomenclature you give, depending on its size, you get it at the end of the continuous casting process, right? So this is called continuous casting because this is happening, all the time. There is no sort of stationary process taking place. It's happening continuously. It's a transient process. So that is why this is called continuous casting process, right? So this is the overview of a continuous casting process. So what is the important part of this problem which has been faced by industry, and then because of that we come across to this problem, and we have worked with the industry to get solution of this problem. So this billets, what has been formed here because of the continuous casting is not always of high quality. There is always crack in the billets. There is always because of some problem in the heat transfer, the solidification doesn't take place uniformly, properly, and then whenever this billet comes out of this process, then there is some crack formation happens. Sometimes the billets are not of the size which you want, but it takes some rhomboidal shape because of the ununiform heating, right? Because of the high temperature, there are thermal stresses also which has been evolved in the billets, and because of that, the quality of the steel is not as good as it is desired. So that is why the problem was like we need to design this copper mold in such a way that the quality of the steel which comes out from this process is good enough. So that's the main idea. Now what happens basically in this process, whenever this solidified steel, when it converts to solid, and then there is some shrinkage happens, right? Because it's a liquid which is a lower density, and when it becomes solid, its density is large, right? Density increases, and since density increases, it solidifies. It shrinked to a lower volume, and because of that, in the mold wall and the solidified strand, there is a gap. There's a gap formation happens because all this length. I mean, if you see from this view, this is the complete length. But when it solidifies, and because of the shrinkage, there is a gap which is found here. This gap is not shown in this diagram, but yeah, the gap is not shown here, but I'll show you in some other diagram. So between the mold and the solidified cell, there is a small gap which is produced, and because of that small gap, there will be air and trapped in that small gap, and because of that, the heat transfer rate reduces. Because you all know that air has a very low conductivity, and when there is a air between the solidified strand and the copper mold, then the heat conductivity, because of the lower heat conductivity of the air, the heat transfer reduces, and when there's a reduced amount of heat transfer, then there's an effect of solidification, right? Solidification doesn't happen properly. So that is why the main idea is like that the heat transfer rate should be as high as possible, and you should make your copper mold of such a shape that that gap doesn't happen. So instead of having a copper mold of uniform cross section, industry tried to make a taper at the bottom of the mold, so that because of the taper, the air gap is not there. Air gap is as less as possible, so that heat transfer rate doesn't change, right? Because if there is no air gap, then the heat transfer will be good. And then now the whatever taper they are using, these are based on sort of some experience of their previous work, but there is no mathematical calculations done. Of course, people have been doing. It's not that nobody has done these calculations, but it depends on different cases. Like the kind of industrial mold we have been come across with the industry. Their calculations, the calculation which has been available in the literature, actually the kind of taper they are basically advising doesn't work in this mold, because the conditions are different. Because the taper depends on the rate of circulation of cold air. It depends on the casting speed also. Like the casting speed is basically the speed at which you get this still out from this mold, right? Because at certain rate you are getting the still out of this mold, so that is called casting speed. So this gap depends on all casting speed, the water circulation outside, and of course like the size of the mold, then the material which has been used in the mold. There are several things on which it depends, and because of that, this air gap basically can be different in different cases. And since the air gap is different, so the taper can also be different depending on conditions. So that is why there is no any sort of thumb rule that your taper should be something like that. There are thumb rules, but it doesn't work for all kind of molds. So that is why our intention was to find out a sort of appropriate taper, so that the air gap between the mold and the solidified strand is as minimal as possible. Because if you put more taper also, then also there is a problem. Because if your taper is large, then again it will basically give pressure in the solidified strand, and in that case you will again get crack in the billet. So that is why your taper should be as perfect as possible, so that your air gap is also not there, and then there is no additional pressure from the mold to the solidified billet. So that was the main sort of objectives behind all the projects we have been doing in the last several years. And then of course we are sort of evolving, like we have worked with billet billet casting, then now we are working with thin slab casting. So there are depending on the size of the solidified steel, as I told you, it can be billet, it can be thin slab, but their geometries are all different. The mechanism of cooling the molten metal is also different. So that is why all this modeling and all this CFD analysis is different depending on its shape and size. So that is why it's not like a single problem you do on modeling and that will work for all kind of casting processes. It's not like that. So that's the background which was important to understand, explain you, because without that, whatever explanation I'll do after this one would not give you any interest. So I don't make my slide very much technical, because you may not be able to understand, because you will be all from different background, and this is a particular area of research, so you may not have any background. So I will try to give you an overview of this casting process, so that you have something in your mind to understand. So these are the engineering issues which happens with continuous casting process. The first one is like the distortion of mold. Right, mold is that rectangular channel which I have been saying, which is basically sort of the geometry which gives you the shape of that solidified steel, right? So that mold, although it is made of copper, but because of it exposed to very high temperature molten steel, it also gets different stresses, including thermal stresses, and because of that, the mold actually distort after a certain period of time. Right? It may work for 1 month, 2 months, 1 year, but over a period of time, the mold might distort. So if there is a distortion of mold takes place, that means its shape is changing. So all your calculation doesn't work, right? Because you have certain taper in your mind in the beginning of the design of the mold, but later on its shape has changed. So whatever product of steel you get from this mold could be different. So that is why the mold distortion is one phenomena which is important to study. What is the amount of shrinkage, or what is the amount of deformations you get in a mold, right? Because if there are more amount of distortion in the mold, then maybe you have to increase the cooling liquid, so that you can still keep the temperature of the mold at a lower level, right? Maybe the casting speed also has to be changed, so that the mold can last for a longer amount of time. Those kind of remedies can be taken. The second problem which one might get is the breakout or crack formation in cast products. So this is basically the product of the this process. The liquid metal converts to billet or slabs or blooms, depending on its size, as I told you before. So there can be crack formation, there can be breakout also. So this is the another things which is an issue, right? Not only just the mold, but the billet also. Both are important, but both are separate in entity. So you should at least remember the terms. Mold is the that channel through which the liquid metal comes, and the liquid metal which converts to solidified shell, that is basically billet. So there can be problem in both, in the mold, and there can be problem in the billet also, or slab, or blooms also. So rhomboidity of the billets is another problem, which is basically it is not cracked, or there is no breakout, but the shape of the billets changes because of the thermal stresses which it's encountered. So that is another problem which one has to look into. And the other issue is insufficient solidification inside the mold, right? Because if the solidification doesn't happen properly inside a mold, then what may happen that your the strand which will be formed at the outer periphery, that solidified small, thin solidified strand which formed inside the mold, that will be very thin. And since this is very thin, when it comes out from the mold, there is a possibility that it will break. And if it breaks, then there is a problem, because once it comes out from the mold, there is no guidance. It is basically freely going out of the mold, and then you are spraying it. So that is why the insufficient solidification is another problem. But of course, like this insufficient solidification basically brings out the crack formations or breakout, whatever happens. So these are the engineering issues, and then in order to resolve these engineering issues, we take several remedies. So what is CFD here? Why you need a CFD here? It's a smart solution to any engineering problems, right? Any engineering problems you have, it's not always possible to do in terms of experiments. So you do some modeling, you do some simulation. So it's called a smart solution, because without spending much money, you get a solution, and then it helps you to overcome many engineering problems. So there are a few steps which has been written here. The first one is you obtain design and operational data from plan, because you need to know different design data, because whatever problems you are going to solve, you need to know what are the material used here, what are the operational conditions used here, because you need to put those as an input in the CFD simulations. You need to reduce your problem into simpler units, because in industry you have several things happening together, so you cannot solve everything together, right? For example, this problem, if you start from Tundis, then you do solidification in the mold, then you go to spray cooling. So if you take everything together, then it's a big problem. It's very difficult to solve the whole problem entirely. So that is why you should try to decouple the problems into several small parts, so that you can get solutions in a less amount of time. Understand the physics is very important, because without understanding the physics, if you try to apply CFD problem, then what will happen? Then you will be considering some of the phenomena. You may not considering the some of the phenomena. So it's very important to understand the flow physics of the problem, heat transfer of the problem, and then accordingly use different equations which are available. Even you are using a software, because we have also used software, we have also developed code, but even you are writing using a software, because in a software you have all tools available, but you should know what are the tools required for you, right? It's not that CFD means you solve momentum equation, energy equation, all equations together, and then you use turbulence model, whatever is there, but it's not like that, right? You have to choose the proper equation which is important for this problem. You need to choose what are the proper boundary conditions which basically works for this problem. And of course, there will be few things which will not be available in the software. Then you have to write user-defined routine for those additional things, right? Because every problem is specific, and for every problem you need to sort of need some additional things which may not be available here. Then you use CFD methods to simulate the actual problem, and then analyze the results, whatever you have got, and based on your now these physical results, whatever you get, then you can incorporate these changes in the industry, right? So that's a big gain, because little bit of modifications can give a lot of earning of revenue, a lot of the industry can recover from a lot of losses. So that is why these molds, like if they are cracking after some time, they are deteriorated after some time, so then they buy this mold in bulk. So after 1 year, like if all these molds are not working, then there's a huge loss for the company. So if you can design the molds properly, then there's a huge amount of saving for the industry. So that is why if you see, all industries are these days does some sort of numerical simulation. CFD, like some 10 years before or 15 years before, CFD was sort of a area where only few people works. The very few people in academics or some industries people work in CFD. But now if you see, everyone is working in CFD, because the commercial softwares are available, and this has been made very friendly. And because of that, people are using in many applications. You just pick up any of the applications of heat transfer and fluid flow. People have been working CFD. Starting from bioheat transfer, starting from aerodynamic design. The all processes. The chemical processes, fire problem, in the atmospheric problem. Simulation of even computers and everywhere. CFD has been a big tool these days, and I'm sure in this course people have given you overview of this kind of problems. So the next is the phases of research, what I'm planning to discuss here. The first one is like I think this diagram is little more elaborate, so I have to again explain you this diagram here. So this is the jet through which the liquid metal comes. Normally from the Tundis, through a jet, the liquid metal is poured into the mold. So this is the jet through which it is coming, and this is the liquid still. And in between, if you see that yellow dash, that is the solidified shell, which is I am mentioning as strand. This is solidified shell or solidified strand. This is called shell because this is only at the outer periphery, right? This gives you sort of a solid boundary, and then inside that you have liquid metal, right? Because initially you have only a solid shell in the beginning, and then gradually everything becomes solid. So that takes some time. And if you see here, there is a air gap. That white color which has been shown here is a air gap. Why it is happening? Because this solidified shell is basically compressed because of the change in density. There is a shrinkage, and because of there is air gap formation, and because of this air gap formation, the heat transfer affected. So if you can make your mold slightly, tapered to the inward side, then this air gap will reduce. And if this air gap is reduced, then your heat transfer will be very good. So that is why you need to do numerical simulation to predict this air gap. So that's what we have been doing in the recent times. Now, the first thing is like, you can solve this whole problem together, right? You put boundary conditions outside, you solve the heat transfer equation, conduction equation inside the mold, then you have whatever convection in the air gap, then you have a solidification, whole like momentum equation and energy equation for this molten metal. And then, of course, like when there is a solid, then you don't need your momentum equation, so you have to switch up your momentum equation. But in this portion, you need a momentum equation. There are turbulence also, so you need to use some turbulence model also. So all these problems needs to be solved together. Again, like you have a cooling water flow, so for cooling water flow also, you have to model it appropriately. So there are several issues, several problems together in this. So as I told you before, it's always good to sort of decouple or like make your problem little smaller so that it can be done effectively. So in the first phase of research, what we have done, we tried to find out the interfacial heat flux between the mold and the billet, right? So at the interface, at the inner surface of the mold, if you see that red color strip here, that's the mold. So the inner face or the hot face, the outside is called cold face of the mold, and inside face is called the hot face of the mold. So that inside face, which is called hot face, we try to find out the heat flux. What is the heat flux there? So if you know the heat flux at the inner face, then basically the mold problem can be solved separately, because you have a heat flux boundary condition at the surface of the mold. Outside you have a convective cooling condition, and there is heat conduction in the mold. So the mold problem can be done separately. And the inside problem, the solidification of the billet or solidification of the slab, which is inside, can solve separately again using the same interfacial boundary, interfacial heat flux in the mold. So you are separating problem into two different problems. One is with mold, with the boundary condition of heat flux, and for the billet, another problem with a heat flux boundary condition at the interface, because interface for the mold and billet are same. So that is why you can use the same heat flux for both the cases, but both the problem can be separated out for this case. So the first thing what we have done is that we have found out the heat flux at the interface from the experimental data which has been got from industry. So once we have the heat transfer profile, heat flux profile in the hot boundary of the mold, then we can get all the temperature profile, because you can solve the conduction equation for the mold, and then you get a temperature distribution inside the mold. So once you have the temperature distributions, then you can solve a thermomechanical model in order to find out the mechanical stresses, whatever the mechanical stress developed here, what are the thermal stresses developed here. So you will be able to do that part, which is not CFD. This is like we have used NC structure to find out these deformations. Of course, we are not expertise, but we have used it, using that software, taking help from some of the faculty who works in this area. So then from those mold stress, we can find out the deformation. What is the shrinkage of the mold? right? So that has been done in this problem. The final deformation of the mold using thermomechanical model. Then the third phase, what we have done, we have developed a turbulent flow solidification model, because this is not laminar flow. We have used the turbulent flow solidification model for this problem, inside problem, with the same heat flux which we have predicted. And finally, based on this two problem, like here also you can we have find out the deformation or shrinkage of the billet. So once you know the shrinkage of the mold and you know the shrinkage of the billet, from that you can calculate the taper. What should be the taper of the mold, right? Because the billet will also shrink to a lower volume. The mold will also actually, it bulges outside. It goes outside because of the deformations. So the mold goes little bit outside, and the billet moves in because of the shrinkage. So there is a air gap. There is a gap which formed here. So then we are able to predict that gap, and based on that, we have sort of give a recommendation to the industry to find out the taper. So that are the different phases, and beyond that, I will also explain you that without finding out the heat flux, the whole problems we have solved together, that all mold and billet can also be solved together, which is an integrated sort of a problem. And then we have done 2D analysis of that, and we have done 3D CFD analysis of that also. So there are several phases we have done for this problem, which we'll try to explain very a comprehensive way. So this is the first part of the problem, where we have used the inverse technique to find out the heat flux. So you take any mold, like this is the, again you can see the mold here, rectangular mold, and liquid metal is coming from top and going out, right? So you take any section of the mold, and this is the section of the mold which is shown here, a section of the mold. And from the industry, actually, they use certain sensors, and from those sensors they get certain temperature data in the mold. Now in this problem, we know some temperature data, and the boundary condition, heat flux inside, is not known to us, right? Because that is we are going to basically predict in this problem. So the boundary heat flux at outside is not known to us. This is unknown to us. And the outside of the mold, the cooling condition is known to us, because we know what is the water flow rate. We know the properties of water, so we can calculate convective heat transfer coefficient. So we can have a convective boundary condition inside, outside of the mold, right, which is outside, but in this case, left-hand side, the water is flowing here, so we can have a convective boundary condition here. So these are all known conditions. So this boundary is known to us. Boundary condition is known to us. Upper and top and bottom, these can be considered to be adiabatic, because there's a very little losses of heat through these two boundaries, because the heat transfer is dominantly happening in this x direction. And only thing is, like this heat flux, which is unknown to us, we need to calculate, right? So in a direct problem, you cannot solve it, because in direct problem, you need to know your boundary conditions, right? So it's an inverse problem. So we have some information about the temperature. So we use conjugate gradient method, and then using the conjugate gradient method, we determine the heat flux at this mold, right? I think Dr. Ajit Parwani has given you a lecture a few days before. So he worked with me for inverse problem. He was the first PhD student who worked with me for inverse problem. Of course, Mitesh is the first PhD student, but he worked in some other problems. But Ajit has worked with this problem, and we basically worked with conjugate gradient method from that time. And of course, like for this part of the problem, the another student, Dr. Udairaj, who is a faculty at IIT Vilai now, he has done this part of the problem, and he has predicted the heat flux using conjugate gradient method. So I don't discuss about conjugate gradient method, because that is another sort of a lecture. So in this problem, basically the two-dimensional heat conduction problem. So the Laplace equations there, and in an inverse problem, basically you assume certain heat flux in the beginning, because the boundary condition is not known to you. So that assume heat fluxes you will get certain temperature distribution. So that's the T, and these are the temperature which has been measured by the industry, and the data has been given to us. So whenever you can, whenever your heat flux estimation is correct, then this difference will be very small. It will goes to 0, and then your basically that's your objective function. This is called the objective function of the problem. You assume certain heat flux. From that heat flux, you get certain temperature distribution at certain points, and from those certain points data you compare your measured data and the predicted temperature. If they are matching, then your objective function is basically satisfied. But that doesn't satisfy so easily. So you have several iterations in order to get a good heat flux which will give you these objective functions equal to 0. So that part is like you have to solve several problems like sensitivity problem, adjoint problem, and gradient equation. This equation and this different equation needs to be solved under these different problem names, and from that you basically predict a heat flux. So I am not discussing that much. These are the temperature informations we have got from the industry. At different points they have measured from the operational plant what are the temperatures, and from that basically we have predicted the heat flux in the left hand side. It was a challenging problem. It was not easy to predict the heat flux in the hotter side, but eventually we are successful to get these heat fluxes using that method. So these are the plot of heat fluxes. Like this is at the top, which is called the meniscus of the that liquid metal, and that's the top of the mold where heat flux is very high because the high temperature molten metal just enters the air. So that is why heat flux is high, and gradually it decreases. So we have estimated. You can see plots, and then there are correlations available in the literature also, which are from other kind of casting. So, but of course, like there is certain agreement which won't be exactly same because this is a different mold, and correlations are mean for different kind of slabs. So, but then still we compare to have certain idea that we are not getting some abruptly different results, right? Then this is the thermomechanical model, which I don't discuss much because this is another domain which you may not be familiar. So the thermomechanical model, first you have a thermal model, because the heat flux is known to you from the experiment, from the inverse problem. So with that boundary conditions, you do a simulations, the 3D simulations you can see here. We have taken only one boundaries because these are all symmetric. So instead of taking the whole domain, you take a slice, and then you see there's a arrow here shown here, there's a mark here. So this is the domain which we have solved because it is a symmetric problem, and then that has been shown here. So inside the mold you have a heat conduction, transient heat conduction equation, and then from that prediction of heat flux which we have got from the previous problem. So that actually extrapolated to a two-dimensional plane, because we have only got in a one-dimensional plane because we solved only two-dimensional problem. This is a three-dimensional problem. So heat flux normally is almost constant along this direction. Only at the corner the heat flux is little less, which there are standard relations between the heat flux at the corner and heat flux at the off-corner region. So using those standard relation, we have predicted the heat flux all along this line, right? What I'm saying, like the heat flux from the inverse problem is known along this direction. Now, this is a three-dimensional problem, so you need to know in this direction also. So that basically in this direction it doesn't vary. So whatever values you have got in this direction, same is copied in this plane, but only at the corner we have taken certain reduced amount of heat flux, right? So by that we solve the this is shown the corner heat flux, this is the off corner profile which we have got, and then the corner profile the heat flux is slightly lower. So that is why there is a difference between the heat flux between the corner profile and off corner profile. So that is certain relation people uses. We have used this relation, but it's not that later on actually we have predicted corner heat flux also. Initially we have used this relation for this mechanical model, but later on another student who is working on inverse heat transfer. He has worked with prediction of this one. And then we have basically corner heat flux profile also. So yeah, so with this thermal model, whatever temperature distributions we have done. Okay, so I'll come back to this one also because I have taken this slide. This is another student, Anand Srinivasan, who is doing his PhD, almost at the end of his PhD now with me. So he has actually done a two-dimensional analysis, and he has a different kind of mold where we have actually temperature distributions not only along this direction, because in the previous problem I have shown you, we know temperature data only at the y directions, but in this problem we have temperature in the x direction also. We have a lot of thermocouples in this industrial mold, which we have got, which data we have got from the industry. So then in that case we are able to do a three-dimensional simulation of inverse problem, from which we got heat flux profile. Now if you see, there is a variation of heat flux from center towards corner. So at this 0 is like center, and towards the corner it gradually reduces, right? Distance from center towards corner to corner. This is almost like at the corner 0.7, and this is at the center of the mold. So starting that, this is the center of the mold here, and then you are moving towards this corner. So that's what is shown. So heat flux doesn't change like the way we have shown in the previous slide. There is a drastic change. This doesn't happen like that, right? It gradually changes. So here you see corner to off corner profile, they are all same, but suddenly there is a change. But where in this case, the heat flux changes gradually from corner to the off corner region. So that's the prediction he has done with his inverse problem using some other technique. It's not conjugate gradient method. He has used some other technique, and he has also found that, at least he has found that the corner heat flux is different than the heat flux at the rest of the domain of a mold, right? So that has been predicted by the student. Now again, going back to the temperature profile, we have solved the mechanical model where different stresses has been incorporated in the ANSYS mechanical model, the elastic, plastic, thermal, and creep stress, whatever stresses may encounter in this problem. And from this we have calculated the total stresses, and from there we have calculated the deformation of the mold, right? So there is some result validation we have done with this literature so that our mechanical model is correct. So there are two validations we have done. I am just showing you for this problem, and then from that basically we have predicted the deformation of the mold. So I'll again come back to the deformation of mold to a later slide, but then now we are going to discuss about the turbulent flow simulation inside the mold, because the previous discussion was the heat transfer in the mold. Now heat transfer in the billet, which is basically the central portion where molten liquid is solidifying to solidify. So that's the portion which we are going to discuss. So in this case, we have solved three-dimensional transient turbulent flow model, and the basic continuity, momentum, and equations needs to be solved here for the flow field, and for of course for the energy, we have a energy equation. So what is done here in this case, because there is a solidification which is happening here. If you see this diagram, this is a general diagram of a solidification model taken from ANSYS Fluent, what is called the database. And if you see here, there is a solidified shell here, and then the gray color which is shown here, this is a massy zone, right? In this zone, actually, it's not completely solid, not completely liquid. It's somewhere in between solid and liquid. So that is why it behaves like a porous media. It's called massy zone, but the modeling of this massy zone is done through porous media, assuming it to be a porous media. So we have porous media simulation for this massy zone. Solidified shell, we need only energy equation with sort of conduction heat transfer. There is no heat flow here. There is no flow here. And this part is basically your liquid metal, where you are solving whole momentum equations along with turbulence model, and of course energy equation also. So basically, this billet has 3 different region, right? This is complete liquid region. This is massy zone, which is a mixture of liquid and solid, that is why it is called massy zone. It's not completely solid, not completely liquid, which we treat as a porous media, and this one at the outer periphery is the solidified shell. So the momentum equations are all as usual. Only thing is like we have a source term here, which is important for this massy zone because it works as a porous media. So you need an additional pressure drop because of this massy zone. So that is why this additional sink term is added in the momentum equation, right? So that's the additional modeling term. I don't go to the very much detail of these equations, right? So these are the equations which help solve, and these are the turbulent equation which we have used. We have used realizable K-epsilon turbulence model because this is basically good for swirling flows, and of course we have tried with other turbulence model also, and the convergence was very difficult with other turbulence model, and finally we converges to this turbulence model in this problem. Then for the heat transfer, this is the energy equations. Now, of course, like the heat transfer here is a phase sense process. So you have both sensible heat transfer and latent heat transfer. So that is where the enthalpy is like sensible enthalpy and latent enthalpy. So if you add the sensible enthalpy and latent enthalpy in the energy equation, which is given in terms of enthalpy H, so you get a sort of enlarged energy equation or more detailed energy equation, where you have certain extra term, this one, which is coming because of the latent heat, and this is another term, advection term, because of latent heat. So these are the 2 equations, 2 extra terms you can find, which are basically termed as source term in the energy equation because of the solidification model. So this is the energy equation which needs to be solved here, right? The F is the liquid fraction, right? When it is completely liquid, then value of F is equal to 1, and when it is completely solid, then it is 0, and in between this is calculated by T minus T as the Solidar's temperature. That means the temperature at which still solidified, and TL is the liquidus temperature, that is the temperature at which still become complete liquid, so that TL minus TS. So this is sort of a porosity in this problem. So you can view it as a porosity in this problem. So which is liquid fraction, which is important here, right? So we have of course validated our model, numerical model, for a circular mold, right? Our mold, I have shown you that all like these molds are rectangular mold, square or rectangular mold, but we did not find any result available in the literature which is very close to our simulations. We have found a round mold, and then for round mold we have done simulations, and then we have validated the numerical results of literature. Then this was the overall sort of sequence of our problem. The first thing, like we get mold temperature measurement from the industry. Then we have used inverse heat conduction model. Using inverse heat conduction model, we have predicted the heat flux profile at the interface of mold and billet. Then we divide the problem into 2 parts. One part, we do a elastoplastic and creep thermomechanical model of the mold. That means this gives us the deformation of the mold or distortion of the mold. And second part, we do a turbulent flow and heat transfer analysis of the billet, and from that temperature result, we do a billet shrinkage analysis, right? Here we have not done any mechanical analysis because from the temperature distributions itself, there are relations, standard relations available, which we have used here to find out the shrinkage of the billet. Of course, we can do a small, mechanical model here also, but then that requires more amount of involvement. So for that time being, instead of mechanical model, we have used standard relation to find out the billet shrinkage from the temperature data. And now you have the billet shrinkage and mold distortion. So both these deformations are present for us from that we have predicted the mold taper. So that is the final goal which we have done in this problem. So there are some results which we have, which I am showing here. These are the results for the mold. You can see here the inside of the mold is hot, right? Because the molten liquid is flowing through this mold. So that is why you can see this is the red colors is extremely hot, close to the meniscus. This line is meniscus line because meniscus means that's the surface from which liquid level starts. So this is very hot and gradually it cools down, and outside is sort of cold because there's a water which is flowing outside the mold. But of course this part is little hotter because again this is at the top of the mold. So if you see the temperature is in the mold is like outside is not very high, somewhere in the range of 400 to 450. And from these temperature distributions using mechanical model, we have calculated the displacement in the mold. So if you see the displacement in the mold with the contour, you can see the displacement are higher at the top of the mold, which is close to the meniscus, and gradually it decreases. So that's what you can see from here. But of course, like the displacements are very small. If you see here, something to the power minus 10 to the power minus 5. So the deformation of the mold is not very much, as we are thinking that there can be a lot of mold deformation, but mold deformation is very small compared to the deformation of the billet. Although whatever millimeter deformations, or micrometer deformations we have, and that is also important to have an accurate model. So that's what is shown in graphically also here. The center line is deformations is little less than the corner line, and from the meniscus to the exit of the mold, these deformations are shown, and all these deformations are not same everywhere, right? This is the meniscus. It's 0 because it's the beginning of the mold, and gradually it increases, and then after that it starts decreasing gradually, right? So that's what you can see from this diagram, and based on that we have predicted the top taper of the mold. This is the so this is the temperature distribution shown of the billet, right, which is the inside portion, the solidified liquid, right? You can see here the exit of the mold, this liquid is still at a high temperature, somewhere in 1823 Kelvin, and the outer periphery is solidified. That is why those are at the somewhere in like 10,000 in this, or 1,000 in this range. But the solidus temperature of steel is higher than that. So these are still at a high temperature, but still they are solid, right? So that deformations you can show here. And this one phenomena from which we have observed here, that there is a remelting zone which happens somewhere at the middle of the mold, because you can see here also the jet comes down at a high speed, and because of that again it starts solidifying from the top. This is the meniscus. It starts solidifying, but because of this high jet, this actually strucks at the boundary of the mold, and because of that flow, again the solidified cell remelted here, and then again it becomes liquid here. So that is in this diagram also you can see this blue color. This is cell thickness. This is the cell thickness. This is cell thickness, and you can show here for this one. This is increasing. Temperature is increasing, so cell thickness is increasing. Then it starts decreasing because of the remelting. Right, because of the remelting, it is decreasing, and again it starts increasing from there. So in between there is a remelting zone. Right, this is happening because of the turbulent flow which is happening here. So I have even better diagram which can show the remelting thing. And then at the end of the mold, you can see this solidifies thickness something like 0.01 meter, right, which is like something like 10 millimeter thickness of the cell which we are predicting, which is very close to the mold thickness one gets in an industry. So these are the, based on our observations, we have actually suggested them about different tappers which can be used. The existing design, they have a continuously decreasing, continuously decreasing size of the mold. The tapper is like sort of uniform from top to bottom. This is distance from mold center to the face center, and this is distance from the mold meniscus level. So if you can see here, the distance is gradually decreasing. That means your tapper is uniformly uniform. Tapper is from top to bottom. It is uniformly uniform tapper is given here. But what we are basically suggesting them that you should have different tappers for the center, and you should have different tappers for the corner, and it should not be sort of a same tapper everywhere. You should have a tapper, more tapper at the beginning, close to the meniscus, because there are more deformation in the beginning. Followed by that, you don't need any tapper for certain portion, which is basically a remelting portion. And after that, you should again have a tapper which is not at the same rate as at the beginning, but at a slower rate. You should have a tapper. So these all these sort of percentage tapper and all these calculations are, we have predicted for this problem. So now the summary of this part of research is given by this one. This I think I don't again explain this one. I have few more things to show you, which I'll show you in the next part. I think I have another 10 minutes of time it is, right?
Yes, sir.
Yeah. So what I'm planning to show here is that we have done this problem. The previous cases, what I have shown you was like basically we have break the problem into two parts. One is the mold part and one is the billet part. And then using the same interfacial heat flux, we have calculated the mold tapper. But the problem or the limitation with the previous model is that you need certain experimental data, because once you have the experimental data, then only you will be able to predict the interfacial heat flux. So if you don't have interfacial heat flux, then you won't be able to do that problem. And getting interfacial or getting experimental data for every problem is little difficult, because you need to do experiment for all kind of problems, and then you have to predict temperature, predict heat flux from temperature, experimental data of temperature. So that is little sort of not possible always. So that is why we have predicted or we have developed another model where actually you don't need experimental data all the time. You need to do experiment once. From that you get certain information, and from after that, without experimental data of temperature, you'll be able to simulate the mold. So that's what I'm trying to discuss in this 2-3 slides. So this is the sort of a, let's say the strand inside the mold. That's the billet what I'm talking about. And this is a two-dimensional code which has been developed by my former PhD student, Dr. Saurabh Chakraborty, who has recently finished his PhD with me. So this basically most of the work has been done by Saurabh in his PhD thesis, and then of course another student, Jaya Krishna, is also working now, who is basically doing the CFD of these problems. So in this work of Saurabh, what he has done, he has developed a code. It's a two-dimensional simple code. So what he has been done, because a two-dimensional code, it's a three-dimensional problem. So what he has done, like he takes a two-dimensional plane, and then with casting velocity, he marches towards the exit of the mold. Right. So instead of solving the whole problem as a steady-state three-dimensional problem, he converts it to a two-dimensional problem with a transient conditions, like with in a two-dimensional problem with marching with certain velocity. Right. So that's what has been done here, and the grid is not important to show you. So what he has done, this is like the governing equation. This is only two-dimensional heat conduction here. This is the transient term, and this is of course the latent heat, latent term, the source term, which is required in the energy equation because of the latent heat transfer. So this term is basically gives you the sensible part. This term gives you the latent part. So this and then overall with this, he marches in the z direction with casting velocity. So the other things which is important in this problem is the boundary condition, because in this case we don't have any heat flux information. As I told you, we don't work with the heat flux informations. Instead of that, what we do here is that the outside we have cooling water, and then we have a thickness of the mold, and then there is a air gap. There are three things. There are three resistances here in terms of a boundary, right? If you think about resistance network problem, outside the solidified strand, you have one air gap. After that, you have a mold there which has certain thickness, and outside you have a cooling water channel. So there are three things which gives you certain resistances. So if you can calculate all these resistances, based on your resistance network analogy, you can calculate the total resistance. Once you know the total resistance, from that you can calculate the overall heat transfer coefficient, and that overall heat transfer coefficient can be considered as a boundary conditions, and you can only solve the billet problem with that boundary conditions. Mold will not come into picture here, right? You don't need any interfacial heat flux condition, because now your boundary is actually cooling boundary, and you have a convective boundary condition now here, right? So there is no heat flux required now. So only overall heat transfer coefficient, you have three terms. The resistance is 1, 2, and 3. This resistance, first resistance, is basically the resistance because of the cooling channel, mold to water, MW, one resistance which is outside the mold, which you get because of the boundary layer, because of the cooling waters there. This is the resistance because of the thickness of the mold, right? Only a problem with this resistance, which is basically because of the air gap. Although you don't need interfacial heat flux here, but the problem is that you need certain, you need this resistance. This is not known to you. Now this air gap, Saurav was able to calculate by using a simple mass balance, right? He was able to calculate the shrinkage, or this gap which is formed because of the shrinkage of the solid material. He does a simple mass balance, and from the density difference, he was able to calculate this Tg from the model, right? So he used these relations from the mass balance, and every iteration he calculates what is the air gap forms because of the contraction of the liquidified metal, right? So that Tg is known to us from the simulation. Only unknown is basically this Kg, which is basically the conductivity of the air. Now the conductivity of air is known to us for sure, but the problem is that air is not really air. Inside that air gap there are gases which form because of the whatever additives which are added there in between the slab and the mold. There are some oils added there, so that that billet doesn't stick to the mold. So some amount of oil is added there, and because of that, at high temperature, that oil evaporates, and there is cracks happens of the oil, and because of the certain gases which basically formed there, and because of that, the conductivity of it's not just air, there are certain gases there, and because of that, this Kg is actually slightly different than air conductivity. It's higher actually, conductivity is higher, and again in that gap there will be some radiation heat transfer, because that's at a very high temperature. So only thermal conductivity is not good enough. You have to consider the radiative heat transfer also. So that is why this conductivity is basically what we have done. We have not given any value. We have calculated this conductivity from the simulations, because for certain calculations or for certain problems, temperature data and interfacial heat flux is known to us, right? So using those interfacial heat flux, and from this problem also we can calculate interfacial heat flux, right? We compare those interfacial heat flux, and we see for what value of Kg those interfacial heat flux matches, whatever values of Kg, the interfacial heat flux matches, those Kgs are considered to be a reasonable value of the conductivity of the gases, or the effective conductivity of that small gap. Now, once you know the conductivity of that small gap, then after that everything is any simulations you want to do, you will be able to do that, because this was the only unknown in the entire problem which has been done, because for a particular case of problem, the whatever oil formation or gas formation happens there is same. So this Kg can be considered in all kind of problems to be same. This Tg will be different, so which we are anyway calculating. So this problem becomes much simpler. So you don't need experimental measurement of temperature at all the time. From one measurement of temperature data, you will be able to predict this Kg, and then you can do it for any kind of casting speed, any kind of for other different for other parameters. So these are the some simulations which we have done, and then if you see the Kg values, we have actually conductivity of gases, we have varied from 1.8 to 2.2, which is not very we have not given, I mean, we don't have to use a very drastic ranges of Kg value, it's only from 1.8 to 2.2, and this is the simulation with known heat flux, which we already know from our experimental data. And if you see, they all matches, and I think the values of Kg is equal to 2 is considered to be best one, because we have also compared with the solidified cell thickness. And if you see, the black color is the simulation with known heat flux from experimental data. So if you see at the end, the solidified cell thickness is very good. It matches very nicely when we assume Kg is equal to 2 watt per meter Kelvin. Although all are good, but 2 watt per meter Kelvin is somewhat close, very close to at this portion. Here they are not matching much, but at the outlet of the mole, matching is more important, because that gives you basically prediction of the solid cell thickness. So that is why it is considered to be the best one, right? So that's the overall two-dimensional model, which is much more successful, and of course we have published paper on that also. And then we have also done 3D model, like the other student Jaya Krishna is working with the 3D model, where we have done basically three-dimensional simulation of the mold. I am not going to discuss because I don't have time now. So in a 3D model, what we have done is like the three-dimensional simulations we have done. The same problem. Now we are not doing it like a two-dimensional problem and marching in the the flow velocity direction, marching in the from top to bottom. It's not like that. Now it's a steady state problem with a three-dimensional mold, and we have done it in Fluent, and then we have got similar result, but many things you can see from CFD results, that this remelting phenomena which we have observed previously, this 2D model is not able to do that, because in 2D model there is no turbulent flow simulations, right? Only in 3D model we have fluid flow simulation, so this gives you more insight, but of course at the expense of large amount of time. The remelting, you can see here the recirculatory flows, because of that the flow comes from top, and then because of the high velocity there is a suddenly there is a recirculation happens here, and because of that again the solidified cell starts melting in this site. So that is why break and that shrinkage and heat flux changes happens in this region, which is a interesting phenomena which we have observed. No one has observed in billet casting. People have observed in other casting, but in billet casting we have observed this another important issue in this problem, right? So some of the results I'm not going to discuss anymore. So we have done here. There is 3 students which who has
Hello. Sir, you are not audible. I think there is some network issue. Please stay connected.
I think I lost my connection somewhere. Now I can be able to realize when we finish the lecture. Can you tell me when I lost the connection?
Just at the acknowledgement side, sir.
Oh, then it is fine, right? Because I finished my lecture and then I opened this and then I saw I'm not
Yes,
able
sir.
to. Okay, then acknowledgement is fine. Like okay, the acknowledgement is actually important because I have used my student work. I'm just sharing them.
Yes,
Yeah,
sir.
that is not wrong. I mean, that is not correct. Your screen is visible now.
Yes, sir.
So these are the student who has actually worked with me. Dr. Saurabh Chakraborty, his PhD, most of his PhD was on continuous casting. Then Jaya Krishna is entirely working on continuous casting with CFD model, who is in the who is basically working in the CFD part of continuous casting, but he's working mostly on thin slab casting. Whatever we have discussed today is basically billet casting. The slabs are of like square shape, but he's working on very thin slab casting, which is another important area. And Dr. Ruderas contributed in the beginning, for the inverse part of the problem, but not the continuous casting part. Only the inverse part of the problem he has done. And of course, I have taken one slide from Anand also. Srinivas Anand, who is a PhD student, is almost like at the end of his PhD, who is basically working on inverse problem and inverse problem in continuous casting also, because he has done 2-3 problems on continuous casting. So these are the people who has contributed to this work, and of course we have published several papers. I have not added. There are few more papers we have published in this area. Yeah, so that's it. If you have any questions, I'm ready to.
So, participants, any questions?
I hope you are able to understand something, because it's not easy to understand. It's a different area. Yeah, I did not make it more technical, because then it will be even boring for you if I make it very technical.
Yes, sir.
But in general, you should be able to understand that these are the areas and these are the equations in these areas which are important. Some sort of feeling, that's the idea.
Sir, I would like to ask one question.
Yeah.
What could be the limitations when we use CFD as a software in such areas?
In this case, it's not a very, from flow point of view, this is not a very difficult problem, right? Because it's a single phase. It has two different phase, of course, like the solid and liquid. But from turbulent flow characteristics and all, it's not a very difficult problem. The challenges in these problems are mostly the domain of the problem, because if you want to solve the whole problem together, people have done the whole problem also together, starting from the meniscus of the mold, and then after the mold also you have spray cooling, and then at the end of the spray cooling, finally you get a final shape of the steel. So if you solve the entire problem, then the main problem is the computational resources. You won't be able to do in a workstation or a small computer. You need a high performance facility, right? So because the domain size will be very, very big. So that is one thing. And this is a problem where you need some mechanical modeling also, because only heat transfer modeling won't give you very good results. So for mechanical modeling, you have to basically couple CFD with the mechanical part. So there are some challenges. For example, if you use COMSOL multiphysics, COMSOL multiphysics is a good mechanical model, but for the flow problem, you have issues because COMSOL multiphysics is not very good for CFD. The way it is good for the ANSYS is good for CFD problem. So those kind of coupling problems comes because you cannot do the CFD part in ANSYS and mechanical modeling part in COMSOL. So that is difficult to work in two softwares together. And if you think about the mechanical modeling in ANSYS, then it's not that good as COMSOL is good. So those kind of practical challenges is there. And writing a code is also difficult for a person, using all the CFD and mechanical model altogether. So those kind of issues are there for sure. But then you need to simplify your problem, and depending on your requirement, you should choose your tool. That's what you should do in a CFD problem.
Thank you, sir.
Sir, this is Ritesh. I just wanted to know one thing. Sir, when molten metal goes in the mold, at that time temperature is very high. Why people have not considered radiation heat transfer in that? Only conduction convection predominantly considered, but radiations, I think, what is the amount of percentage in the literatures the radiation amount is contributing, radiation heat transfer is contributing?
I think the continuous casting, of course, like I have that tendency to see the radiation heat transfer part, but in the continuous casting, they are not using radiation. But if you see the other solidification model of casting, Sakrolaski crystal growth and other phenomena people have studied. I remember from my PhD or postdoc days that people have incorporated radiation in participating media on those models in back in like 2000 back in 2003 2004. People have been using radiation model, but those are casting, not continuous casting. In continuous casting, the people are not using, maybe because of the molten metal. Even there is a radiation heat transfer, but outside you have a solidified strain, so your radiation heat transfer is not going to penetrate through the solid, right? So there is no chance that there is a radiation heat transfer happen from the liquid to the mold. This is not possible. Only in the air gap there can be a radiation heat transfer, which we have incorporated with certain simple surface to surface radiation we have considered. But here, the mold is not radiating to the ambient. There is no chance that mold is radiating to the ambient because this is in a closed conduit, and whole liquid is basically surrounded by solid. So that is why, the temperature delta T, there is no scope that there is a radiation which can occur from the liquid to the ambient air. So that's the main reason I think radiation has not been considered.
Thank you.
Sir, I have a question.
Yeah.
Sir, you said that the shrinkage will happen in the casting. Sir, we have the problem, and we can overcome the problem of shrinkage by making a bigger mold. So, what is the difference between means using CFD? What are the advantages?
No, the shrinkage will definitely happen because your liquid is converting to solid. So its shape will reduce, right? Because solid has a different density. So that shrinkage is going to happen. The only problem is that because of shrinkage, there is a air gap forms between the mold and the billet. So that air gap is not desirable because of that air gap, there is a thermal resistance which will present there. And because of that, your heat transfer will reduce. So the main idea of having a taper is that you try to reduce that air gap, because if it is shrink by like 1 centimeter, you make a taper of sort of 1 centimeter so that the gap is not there. The mold is always touching the billet. If the mold always touches the billet, then there is no air gap, then your heat transfer will be always good. So that's the idea. Why we have been trying to design or trying to predict the taper of the problem. And now from the CFD point of view, CFD can give you more insight. For example, the last result, which I have just rushed through, that remelting phenomena or the complete model which I have shown you using ANSYS Fluent, then you get more insight of the problem. But in an industry, doing CFD analysis for all problems is not always easy because it takes more amount of time. So if your idea is to see what is the solidification thickness at the end of the mold, then the two-dimensional model which we have developed, where there is no flow, there is only convection heat transfer. Because the cell is moving at a constant speed at a casting velocity. We have only advection term in the energy equation, but there is no momentum equation solved in that case. So then it becomes a simple problem, and with simple problem, if you can predict certain things which is good enough for your understanding, then these simplified models are always better, because CFD is not always easy to use, or it's not computationally it's not computationally appropriate to use all the time. And like for an industrialist, they may not be interested to see what is remelting, why it is happening, and all. They may not be able to appreciate that. So if they are only interested in thickness of the cell at the mold exit, then a 2D model is even good enough, right? So depending on your requirement, your understanding, so you can choose.
Thank you, sir.
Is there any other question?
Okay, with this, on behalf of Mechanical Engineering of Technology, I would like to thank our session expert, Dr. Prabal Talukdar, sir. We are honored to have you, sir, and thank you so much for sparing your valuable time.
Thank you very much. Thank you.
Thank you. Okay, then I'll leave here.
Yes, sir. Thank you very much. Thank you.
Thank you. Bye.
Bye, sir.